and then he joined here as Director of Academics at Ahlia.
Oh, that's very nice. Glad to know details about him. That's very nice.
Thank you.
I think now 48 people are there. We can start.
Okay, sir.
Okay, sir.
Good day to one and all. Proper knowledge of civil engineering has not only enabled us to build bridges, dams, tunnels, expressways, but also figure out a way to effectively handle traffic congestion, disasters, and other unfavorable circumstances. As a civil engineering student, I happily welcome all of you to this webinar on the topic a special concrete with non-corrosive reinforcement. Now, I call upon Shweta as of SY Civil for the welcome speech.
She is not audible.
Yeah. Shweta, are you there?
Shweta, we cannot hear you. Shweta? Swapna, just call her and ask.
Okay, ma'am.
Sorry for the interruption. Gomadi, I think you can start sharing your screen. I will withdraw mine.
Yeah, sure, Manu.
Okay.
Hello.
Shweta, we can hear you.
A very warm good evening to one and all. Today we are having a webinar session on the topic, a special concrete with non-corrosive reinforcement. I welcome each and everyone for this session on behalf of Civil Department, Ahilya School of Engineering and Technology. First of all, I would like to welcome our chief guest, Dr. Kaumati Murugan ma'am, to this session. We welcome you, ma'am. Next, I would like to welcome our Principal and Director of Ahilya Group of Institutions, Dr. P.R. Sri Mahadevan Pillai sir, to this session. We welcome you, sir. Next, I would like to welcome the Vice Principal, Dr. Krishnakumar Kishore sir. We welcome you, sir. Next, I would like to welcome our HOD, Kripa ma'am, and all other faculties. Finally, I welcome each and every participant who are with us today. Once again, I welcome everyone wholeheartedly. Thank you.
Thank you, Shweta. Next, I would like to welcome our beloved principal, Dr. P.R. Sri Mahadevan Pillai sir, Director of Ahalya Group of Academic Institution, for Presidential Address. So please.
Good evening, our honorable guest, Dr. Komati, my colleagues and dear students. After a gap of so many days, I'm attending a program today because, as you know, I had a minor surgery and was under rest for some days. Maybe I'll have to be on leave for one more week. But today, our civil department, which I'm also a part of it, have requested to attend this program and I thought I should attend. The topic is also very interesting. Dr. Komati is presenting a topic on a special concrete with non-corrosive reinforcement. Corrosion reinforcement is a great issue because you know that the concrete is normally supposed to strengthen over the years. That is the basic nature of the materials of concrete except that of the reinforcement. So the concrete is supposed to harden and strengthen. The reinforcement goes on corroding and ultimately it results in the spalling of concrete. I still remember some years back when I was engaging a session at the NSS College of Engineering on the top floor. All of a sudden a big piece of cement fell down in front of me. At that time there was no additional roof above that building. Now there's a sheet roofing above to prevent that. And it was a heavy piece. Luckily I escaped. It fell in front of me, not on my head. Otherwise you would have got one more Newton. But not only that, everywhere this is an issue. When the Britishers were in the country, they always used the mild steel after acid washing in concrete. That acid washing could reduce the rust on it, but even that I think, even today, there are some places where the acid washing is done. There are some places where the reinforcement is given the cathodic protection, where chemical exposures are expected to be there. All these things are happening, but on day-to-day concreting, the corrosion in concrete is still a major thing. And though in the valuation process we take 65 years as the average lifespan of concrete structures, many places the concrete structure, especially I've seen in the metro cities, after 30-40 years it becomes so old that we doubt whether it will withstand. Major reason being the corrosion in the steel. Added to that, almost 80% of the steel that is available in the country is corroded steel because it is scrap recycled. There are 34 steel manufacturing companies in Palakkad district alone. All of them are using the recycled scrap for steel manufacturing. In India, for that matter, only two companies, the Vaishak Steel and the Tata Steel. Two companies are using. Vaishak Steel belongs to the Steel Authority, which is there in many places. In addition to Vaishak, it's there at so many places. Only these two companies are specifically using original iron ore. Most of the other companies are using scrap steel. Some of the companies only using scrap steel, and this gives rise to only rusted steel. The moment the steel comes out of the rolling mill, it starts rusting. So the age of the concrete is also coming down, and concrete becomes ill, rusted. So we have to think of ways and means in which we can have non-rusting concrete by non-corrosive reinforcement. I think that Dr. Komadi, who is a senior research, is PDF at the IIT Chennai, will throw some light on these aspects. Let us hope that by listening to this session, we'll have some ideas on how to make concrete non-corrosive and special. By that means she'll be discussing about some special concrete. Let us listen to it. I'm so happy that she has joined us for this program, and I also invite her to visit the Ahalya campus whenever she is coming to Palakkad, because the Palakkad IIT is also partly situated in our campus right now. With these few words, I congratulate the organizers for organizing such a nice program. Thank you all.
Thank you, sir. Next, I welcome Jemshia of S5 Civil to introduce our chief guest, Komadi ma'am.
Good day to one and all present here. I am profoundly delighted to take an opportunity to introduce the chief guest for the day. She is none other than Dr. Komadi Murugan ma'am, who is postdoctoral researcher, IIT Madras. She did her BTech in Civil Engineering at SRM Engineering College and MTech in Structural Engineering at College of Engineering, Guindy. She currently works at the Department of Civil Engineering, Indian Institute of Technology, Chennai. She does research in structural and earthquake engineering. She has 4 publications in SCI, Scopus indexed journals, and 14 publications in renowned conferences at national and international level. She won MHRD and UGC DAAD grants for conducting research at India and Germany. Outstanding doctoral thesis from ICI and Ultratech. Professor P.C. Verghese Endowment Prize for Best Outgoing Student in MTech from Anna University, Chennai, and won first rank and University Gold Medal in BTech and MTech from Anna University, Chennai, and Best Paper Awards from the Indian Concrete Journal and NIT Calicut. Once again, we heartily welcome you, ma'am. Thank you.
Thank you, Jemshia. Before starting the session, there are some general instructions. Any queries can be typed in the chat box. All the queries will be cleared at the end of the session. Feedback link will be provided at the end of the section. Without any further delay, I hand over the session to our chief guest, Dr. Komadi Murugan ma'am. Ma'am, please.
Yeah, thank you very much, and thanks for the nice introduction by the team. Thanks to Professor for the kind invitation to visit campus and also throwing some light on corrosive reinforcement. Can someone confirm whether you're able to see my full screen?
Yes, Komadi.
Yes, thank you very much. So without further delay, we can get into the discussions. Today, we are going to talk about a special concrete which is made out of non-corrosive reinforcement and matrix. The content of this presentation will go this way. I will throw a light on what special concrete is all about and introduce this special concrete called as textile reinforced concrete, on which I am working on right now. I will discuss about the components of its characterization, that is understanding its properties, and finally I will also share on the details about its applications in practical scenario. So what is this special concrete? So as such, we know there is something called as this conventional concrete or a normal concrete, which is made up of combination of a certain elements or materials, such as the binder like cement, aggregates such as sand and stone, and also water. As we know, this concrete has a certain strength, durability, resistance to fire, and such other properties all by itself because of its composition and its making. And this is the one which is used for any regular sort of construction. Suppose if there is a required construction which is not so regular, which is not so normal, what we look at is a special concrete to meet the requirements. So the concrete which is used in special and specific constructions, and for this they are engineered, and that is a special concrete. It meets special performance and uniformity requirements, which is achieved by selection of the materials which are enhanced or improved materials, along with the improved methods of mixing, placing, and curing practices. So what we see is one or some or most of the properties of such a concrete is enhanced compared to a conventional concrete. So what we say is such special concretes are used in applications such as high-rise buildings, long-span bridges, repair and retrofits, lining in tunnels, and also in places where we need pervious pavements for drainage purposes. So these are some places or some applications to which such special concretes are used. To look into some special concretes which we actually see or learn about or in day-to-day life, we know about the high strength or high performance concrete, wherein we look at the strength of it by changing its ingredient properties and the method of preparation for something like more than 55 or 60 MPa. And so we know that there are also concretes of up to 150 and 200 MPas, which are used in the construction of high-rise buildings and such structures. Next, all that we see is a concrete called as a colored concrete. These are some illustrations or examples of what a special concrete is all about. So a brief note on each we can see now. So the colored concrete is made for specially and specifically for architectural purposes, again by using color pigments as ingredients with the regular concrete in either the dry or in the liquid form. So what we know is also a self-compacting concrete which doesn't need a vibration, and this is prepared by varying the ingredients such as utilization of superplasticizers, reducing the aggregate sizes, and such other more intricate ingredient details. The fourth one, what we see here, is a pervious concrete, wherein the fines or the fine aggregates are generally evaded, and this consists of mostly the coarse aggregates and the binder content, due to which there are pores between the aggregates, and then this particular concrete is used for draining water or wherever we need a water drainage to be done. So at such places, these are used. Again, we have polymer concrete and lightweight concrete, fiber reinforced concretes, and as such. Today, we will discuss about a particular type of special concrete, which is textile reinforced concrete. So now coming to the introduction of textile reinforced concrete. As we saw from its inception, we know this plain concrete that is there into play, either in the regular construction or in the mass construction, and to enhance its load carrying capacity, what was used is the steel reinforcement to take up the tension in the concrete, because as such we know concrete is good in compression and weak in tension. So we go with the usage of steel rebars as the elements taking the tension in concrete, that is to improve its strength and performance. Apart from this, as an advancement, what we have is a fiber reinforced concrete which may or may not have the regular steel rebars, but the fibers which are added to the concrete improve the ductility property of the concrete itself. So these fibers could be steel fibers or glass fibers, or even at places there are carbon fibers which are used for this purpose. Today we are going to discuss in detail about a specific type of concrete which is called as a textile reinforced concrete. In this textile reinforced concrete, what we have is, in place of fibers or steel rebars, what we have is an engineered mesh or the fabric which is called as a textile, which acts as a reinforcement in the concrete. To look at the comparative advantages and disadvantages of a few known and very famous types of concretes or regular types of concretes which are used now. Coming to the conventional steel concrete, we know that it is advantageous in terms of its load bearing capacity. However, due to the utilization of the steel rebars, in order to evade the corrosion, we have this cover requirement, and due to which the sections of this steel reinforced sections which are made out of this conventional steel reinforced concrete are quite massive, and the size and shape are also restricted in certain cases. As we saw, we have also this fiber reinforced concrete, which may not have, or which may need only a minimal cover requirement. However, the disadvantage what we see in this fiber reinforced concrete in comparison with the concrete which we are thinking to look at today is the efficiency which may be reduced in the fiber reinforced concrete, in the regular fiber reinforced concrete. Suppose if the fibers in it are not dispersed or distributed properly. If the orientation and the distribution of fibers are at very random, or if there is a balling effect or anything of that sort, then the efficiency of the fiber reinforced concrete is essentially reduced. In comparison, what we have in our textile reinforced concrete today is a non-corrosive reinforcement, and the reinforcement is oriented based on the target. For instance, wherever we want the tension load to be taken or the tension stresses to be addressed, we can layer the reinforcement accordingly. So there is a target oriented layering of reinforcement, and especially due to the absence of or the requirement of the cover, we have thin complex and thin composite and complex shapes which can be developed with the textile reinforced concrete. To mention a few advantages based on certain heads, such as we have some structural advantages which are listed as thin sections can be developed, as we saw, because of the cover requirement, as we don't need a cover to be provided in specific to protect the reinforcement, and we do have the design flexibility in this system. Of course, this is corrosion resistant and it shows pseudo-ductile behavior. That is, it shows a good ductility, even though it has a higher strength and it is of brittle nature, and it has restricted cracking in it. That is, the cracks that are formed in this particular type of reinforcement, in this particular type of strain hardening concrete, are very restricted in terms of their formation as well as the width. Very, very thin cracks of micrometer levels are formed, but distributed cracks are formed. So what we say is the crack width is minimized, and so this specific material or the system can be used to develop more of these water retaining and such structures. Environmental wise, because of the reduction in the type, the sections, sizes of the sections, and also the material, what we see is the optimization of the materials, and thus which leads to the reduction in the carbon dioxide emission. Also, the materials used in the preparation of this specific concrete is said to have a high durability, and also we have a reduction in weight due to the less thin sections. Economically, due to all these reasons, we have the low price by design optimization and thin sections, and hence a less transport volume, faster and safer constructions. This particular concrete is also good for the precast or the modular type of constructions with the lightweight components and ease of transportation. Wherever we see the advantages, we cannot rule out the limitations also. We do have a certain limitations in this textile reinforced concrete, and which are the design strength is comparatively, I would say the textile reinforced concrete is good in tension and it doesn't do anything in compression. It is a matrix which takes the part of compressive load, and so the design strength in comparison to RCC, it is quite different based on the working principle or the phenomenon. And suppose if the reinforcement is very flexible, these textiles could be of two types, stiff textiles or flexible textiles. If we are going ahead with the flexible textiles, what we see is a difficulty in the positioning of the reinforcement because of the sagging that can happen. Suppose if there are vertical sections or vertical, it is not as stiff as a steel rebar. The textiles which are flexible is not as stiff as a steel rebar, so it won't stand. So additional arrangements are to be made to make it stand before concreting. Also, this is a new material which is being used very rarely in our country, and also research is going on in abroad, such as in Germany, Dresden, and certain other European countries. So as such, we don't have any design code or a proper manual or a guideline which can help us with the design or the practical application of this concrete. So there is a lack of experience, and so proper engineering judgment is required as of now if this specific concrete has to be used in practice. And handling as such is very, I would say it is kind of critical, because thin sections are critical in handling. So the handling should also be taken care. So these can be listed out as the limitations of this particular type of concrete. See, this textile reinforced concrete has different names at different places where it is researched upon. For example, it is also called as textile reinforced mortar, or fabric reinforced cementitious matrix, or cementitious system, or cementitious matrix grid, inorganic matrix grid, or fabcrete, that is fabric reinforced concrete. It has different nomenclatures at different places of its research or utilization. However, this shouldn't be confused with the geogrid or the geosynthetics, the geotextiles that we use for the soil stabilization works or in the geotechnical applications as such. This is something different from the geogrids which are used in the geotechnical applications. So coming to the components of the textile reinforced concrete, we have two main components in the textile reinforced concrete. The component one is a matrix part, which is called as a fine concrete or the fine grain concrete. Second component is the textile reinforcement. Together, these two form the textile reinforced concrete composite. Looking into why this matrix is a fine concrete or a fine grain matrix, this matrix should have the ability to penetrate between the grids of the textiles. The textiles, what we talk about, have grids dimensions of, say, even 0.4 or 0.5 mm width. That is the size of the grid through which the concrete should penetrate to fill the section, maybe even as less as 0.4 or 0.3 mm. So what we look at, 0.5 or 1 mm. So what we look at is a concrete which has an aggregate size as less than 4 mm, and right now what we look at is an aggregate size which is around like 0.8 to 1.2 mm for textiles of grid dimensions up to 2 to 2.5 centimeters. So the aggregate size is too small, and we call it as a fine grained concrete. This concrete essentially has a higher binder content for better flowability properties and to get better strength and durability. And one system which one advantage of this particular TRC or textile reinforced concrete is that this can be prepared in both the forms, in also the stiff form and also in the flowable form, based on the applications which we can see a little later. Essentially, in our research here, what we use are the cement, fly ash and silica fume as the binder part. The main binders that we use are the cement, fly ash and silica fume. At present, we are also looking at the utilization of ground granulated blast furnace slag and limestone calcine clay cement as replacement for cement, more replacement for cement, in order to reduce the carbon dioxide emissions. And as aggregate, what we prescribe or what we use is the utilization of quartz sand and quartz powder in place of the other types of aggregates. But we can also work with the end sand, river sand or the quarry sand depending upon its availability and also depending upon the economy cases. Apart from this, what we What is present as ingredient in the textile reinforced concrete are the superplasticizer and viscosity modifier to control the flow properties along with water. So what we essentially check in this concrete or the matrix is the flowability of the mix. Suppose if we are using a flow mix, we do the flow test using the mini slump or the flow table to ascertain the properties. Coming to the textile reinforcement, the textiles which are used as reinforcement in the system are called as technical textiles. These technical textiles are formed from fibers which are made out of, say, glass, carbon, aramid, or other polymers. An important components in this textile reinforcement is the coating, which will be elaborated a bit later. We have different configurations of textiles. As I said, we have the smallest, that is this particular textile which I am pointing out. It has an internal grid dimension of, like, say, 0.6 by 0.8 mm. The biggest here, it shows like 25 mm by 25 mm. So we have different configurations of these textiles with different yarn properties. Yarn in the sense, this a single thread which is shown here is called as a yarn. So different yarn properties and different grid dimensions. We have different configurations of these textiles which are available, and they can be chosen as per our requirement. There are also possibilities of engineering the textiles based on our own requirements, based on the design. And we also have very recently, we also have found some manufacturers in our country who can transform the fibers to these textiles based on our own requirement, based on our own engineered designs. Like these textiles can also be customized. So more into the technical textiles, what we say is there are around 12 categories of technical textiles which are differentiated by Textile Tech GmbH Germany. These technical textiles are the ones which are used for non-aesthetic purposes, that is where the function is the main criteria. Here I have shown 12 varieties of technical textiles. For instance, the PackTech are the textiles used for packaging. MedTech, the textiles used for medical applications. Geotech, our geotextiles. Indutech, which the textiles which are used in industrial purposes, and so on and so forth. But what we are interested here to develop or to use in our textile reinforced concrete are the textiles which are called as built-tech textiles. These are the construction textiles which are produced for its own purpose. So the main areas of applications of these built-tech textiles are, these can be used to develop standalone components, both structural as well as non-structural, and as well these are used in the repair, retrofitting and rehabilitation applications. The properties which make them suitable are, they have a suitable strength to weight ratio, they are durable, flexible, they have a good insulation and waterproofing properties. The cracking, as I mentioned previously, the cracks formation or the cracking is very much mobilized with the use of these textiles. And as it's been mentioned since start, it is resistant to corrosion or it is non-corrosive at all. So let us see how these textiles are formed in brief. So what we have are the fibers. We have used or we have seen these small glass fibers or the steel fibers which are used in the fiber reinforced concrete. So here mostly what are used are the glass or the carbon fibers. These small glass fibers are combined together or machined together to form longer filaments. A filament is made up of many small glass fibers joined together, and many such filaments are bundled together to form yarns. Yarns are nothing but the threads. We have the threads in our cloths, right? So the yarns are nothing but the thread. A single thread is a yarn, and these yarns are combined or joined together to form the textiles. There are different methods by which these yarns are put together to form a textile. For example, there is something called a woven fabric. Fabric here means nothing but the textile. So in the woven fabric, what we have is the yarns are woven in the horizontal and the vertical directions, like how traditionally we have this basket weaving and all. So in a similar way, in the woven fabric, the yarns are woven together to form the textile mat. In knitted fabric, it is nothing but the yarns are knitted in a specific fashion, like how we stitch the cloth. We have the stitching, different types of stitching which we do for our clothes. It is of the similar type. Again, we have something called as a bonded fabric. In bonded fabrics, the yarns are placed orthogonal or perpendicular to each other, and they are bonded with each other with epoxy or such other bonding agents. There is an improved production of textile by using which is called as a lino fabric. These lino fabrics are produced using propeller linos, which are highly sophisticated machines. These are used in such a way that the yarns are twisted one below each other or one below and above each other in such a way that they don't come out or fall apart once when they are loaded. Again, these four types, the four types which are shown as woven, knitted, bonded, and lino are 2D textiles or two-dimensional textiles. We also do have something called 3D fabrics, which are woven in three-dimensional form itself. They are formed in three-dimensional form itself, and they are concreted, directly kept in the mold, and they are concreted. So now that we have the fibers which formed the filaments, which formed the yarns and the textiles, if we use these textiles directly in the alkaline environment of concrete, what we understand is the glass in which these textiles are made up of, they get affected by the alkali that is present in the cement or the cementitious environment around, and they tend to dissolve the glass and they tend to deteriorate their strength or the properties, and due to which they show much reduced lifetime or behavior. So this is called as the effect of alkali exposure, which we can see here in the microscopic image, where there is a glass dissolution due to the exposure of this direct glass fibers in the alkaline environment. So what we do essentially is something called as coating. So these textiles are essentially to be coated with certain materials or chemicals which prevent the glass in the textiles to be affected by the alkali that is present in the cementitious environment around. Generally we use a certain chemical such as styrene butadiene rubber or epoxy or acrylic polymers. These are the generally used chemicals which are used to coat the textiles. Here I've shown some pictures where in the first image here, what we see is coating of textiles with epoxy. All of these procedures we have done in our laboratory, and we have tried the coating and development of the textiles, the corresponding textiles. So what we got was the uncoated textiles from one of our partner institutions from Germany, and we tried coating it with the essential epoxy component. And what is generally obtained when we coat a textile with epoxy are the stiff textiles. These stiff textiles are stiff in the sense they are not flexible. They cannot be rolled as shown in this picture here. They are planar, and they can be used in casting the plain elements such as the facade panels or slab panels. So what is shown here below is the coating of the textiles with SBR, that is the styrene butadiene rubber. The procedures are quite different. For example, if we coat the textiles with epoxy, we have to leave the textile undisturbed for like 24 hours, take them after 24 hours and start using it. Like it at least consumes a day. But what happens when we coat it with the styrene butadiene rubber or SBR? We have a specific SBR which is developed for coating the textiles. We have to coat the textile panels with SBR, keep it in oven at a specific temperature and for a specified duration of say 30 minutes. In 30 minutes, what we get is something like this, which is a flexible textile. The SBR coating on a textile results in flexible textiles. So coming to the characterization of the textile reinforced concrete, or essentially characterization in the sense, what we are going to see now is how we are understanding the properties of the textile reinforced concrete, the textile as well as the composites, the mechanical as well as the durability properties. So certain tests are conducted to understand the properties of this textile reinforced concrete. These tests majorly include two types. One is the mechanical test to understand the mechanical properties. such as tension, flexure, and pull out, and the durability test to understand how durable or how sustaining this material or all of the ingredients are in the environment which we intend to use them. So what is generally done is the textiles as well as composites are subjected to the mechanical and durability tests or the characterizations to understand the suitability of their utilization. In mechanical test, what we predominant test which we do in the mechanical category is the tension test, because the textile reinforced concrete is majorly or predominantly used in places where tension is prominent, or such as the panels or the facade panels, or the structures where the tensile loads are more prominent. We use this material as applied to those scenarios. So the tension properties are more important in this TRC. Apart from that, what we do is the flexure test and also the pull out test. In the durability, we check the performance of this material in the presence of alkali and also acid. Why alkali and acid, we will see. Apart from this, what we do is, apart from the textile and composite, we also do the basic characterizations or tests on the matrix and its ingredients to understand its flow properties, compressive strength and tensile strength, elastic modulus, etc. So these images here show the setups which are used to test the textiles and composite. The first picture here shows the electromechanical test device, which has a capacity of 5 to 50 kilonewtons, which can very refinedly and critically test the textile reinforced concrete panels or the textiles itself under tension or tensile load. So the second image shows here the servo controlled hydraulic test systems, which are used to conduct the displacement control test for the matrices which are used for these applications. So what we get is the post-peak behavior of the matrices as well. Both of these are displacement control test systems. Okay, so we will now look into the tension test or the tensile characterization of the textiles which are used for this application. There are two types of grip systems that are shown here. The first is the roller grip system, second is the plate grip system. Why do we need two grip systems? That is because if we want to test the textiles, this characterization is to find out the tension strength, that is the tensile strength of the textile. So if we want to test the flexible textiles, what we use is a roller grip, that is at the ends. In order to hold the textiles, we roll the textiles at the ends, we grip it, and that is the roller grip system. The flexible textiles can be rolled because they can be bent. But if we want to test the stiff textiles, which are, for instance, the ones coated with epoxy, what we do is we clamp aluminum plates or cardboards at the edges of these textiles, and we clamp them together in the grip systems of our electromechanical test device. The tests are conducted as per the ASTM D6637 standards. So what we typically do is we check the single yarn tensile strength of a textile. So this single yarn tensile strength is extrapolated to the multi-rip strength, and also multi-rip tensile strengths are also conducted in order to understand the efficiency comparing the single yarn and the multi-rip, and based on this the tensile strength of the textile is ascertained and it is used for design. So typically what we get is the stress strain behavior from the tension test of textiles. What we see here is for 5 samples, we get more or less a behavior like this. There is a certain scatter depending upon the manufacturing process of the textile. Coming to the characterization of the composite. Now we saw how a textile is tested for its tensile strength. Now we will see how a composite or the TRC composite is tested for its tensile strength itself. So what we refer to here is the RILEM Technical Committee, the RILEM standards, which gave the methods or the steps to do the test. Panels of dimensions 500 by 60 by 10 mm are prepared as shown here. So what we do is panels of this of these dimensions are prepared. There are certain specific molds which are engineered for this purpose. With these molds, what we can do is we can do the stretching of the textiles. For example, if these are whether these are stiff textiles or flexible textiles, we don't want these textiles to sag, because these elements are very thin. Like say these elements are only 10 thick, so they are only this much. So if we are checking the composites with 2 or 3 layers of textiles, we don't want these textiles to sag. So there are specific molds engineered for this purpose, where layer by layer these textiles are particularly stretched and fixed in the molds, and the flowable type of concrete is poured to prepare these panels, which are used for the composite characterization. Again, what we have here is there are two types of grip systems here. One is a fixed grip system and another one is a hinge grip system. Both of these systems are for equal purpose, to understand how the composite works under tension. Both of these can be used in place of each other. So these are just two different ways. In the fixed grip system, what we have is we stick aluminum plates on either end of the panel, grip it in our gripping jaws of the test machine. So there are the transducers, such as contact type axial extensometer as shown here, which is connected to the test panel, and also the non-contact type video extensometer, which actually captures the displacement in the panel once when the test is triggered. So after gripping the panels in the test machine, what we do is we apply the tensile load. We apply the tensile load until the once when the concrete cracks, and we stop it until the load reduction is monitored and shown by the system up to 20% of the ultimate load. Typically, what happens is the concrete starts cracking, and ultimately at peak, the textile ruptures, and beyond peak also there is a certain ductility, after which we stop the test. So what we have typically, this picture shows the regimes of tensile stress versus strain curve under tension for such a composite panel tested under tension. This can be very much compared with the RC behavior, or the behavior of the system with steel reinforced concrete. What we have here is the stage 1, which is dominated by matrix, and this is the crack-free state. Here what happens is, as we start loading the specimen, first the concrete cracks. Before cracking, the concrete takes a certain strain. So this stage is called as the crack-free state, or which is dominated by the matrix. And at the end of this stage, when the panel starts showing the first crack in the matrix, that is a concrete. So there is this first crack formation in the matrix. Again, then from this it moves on to the second stage, where the cracks stabilize. That is, there is a formation of certain cracks, multiple cracks over the stretch of the panel. So this stage is called as a crack stabilization stage, where multiple cracks get formed, and at a point of time they get stabilized as well. They stop forming in the matrix. At the end of it, what we go is to the third stage, which is called as the strain hardening stage. In the strain hardening stage, what happens is the concrete along with the textile in the composite form, it shows the strain hardening properties. At the end of this stage 3, the textile, whether it is a single layer or multiple layer, it once and for all ruptures, and it shows the down peak, start showing the down peak, and that marks the strength of the panel, the tensile strength of this particular configuration of the textile, number of layers along with the matrix. So that is the detail about the tension test on textile. Apart from this, what is done is the flexure test of the composite. Suppose if we want to use this, suppose if we want to do a flexure design for this particular TRC, with this particular TRC, what we require as part of input into the numerical modeling or for the design are the moment curvature properties. So such moment curvature properties, to obtain them, what we do is a flexure test of the composite, where the composite panels, half size of the textile panels are prepared as per the, again, these are also as per the RILEM standards. and we apply the 2-point load to understand the moment versus curvature properties. Also, we do the pull-out test on these textiles on the pull-out specimens. These are specific specimens where single yarn is embedded inside the matrix. Like this is very similar to the pull-out test which we do with the steel rebars embedded in concrete to understand the bond properties. How good the textiles are embedded in concrete and their bond characteristics. Again, these are for the modeling. So that is all about the mechanical characterization. Now we will move on to the durability characterization of this textile reinforced concrete. The pictures here show the study on textile, the alkali attack study on textile, the scanning electron microscopy images. The first image here shows the shows the image of a textile which is zoomed in and taken in the scanning electron microscope. So this is the surface of the fibers. These are the filaments or essentially the fibers which are not attacked by alkali, that is this is before exposure. What happens on exposure of these in the alkali solutions? It seems like the fibers, the glass that is present in the fibers, they dissolve. So there may be question, okay, there is coating on the fibers. If there is coating, then why the fibers are even going to dissolve or the glass is going to dissolve? So what we say is the coatings are done manually or mechanically on the textiles. So there tend to be certain holes or flaws in the coating as well. So what happens is whether the coating is present or not, the glass is essentially attacked by the alkali that is present in the system. So what we do is study the deterioration of the textiles for the exposure in alkali environment, and accordingly now we are working on engineering the matrix, in such a way that the glass dissolution or the alkali, what we call it as an alkali silica reaction, is very much reduced. So that is on the alkali attack. Apart from this, so this is on the textile. Apart from this, what is done is the alkali attack test on the composite, which is conducted by immersing the composite panels. We have seen this 500 long panels which are used for the tensile test. So what is done is these panels are immersed in hot water bath to accelerate the attack. Hot water bath, for instance, for like for 90 days or 160 days of exposure at a certain temperature, like 50 to 60 degrees Celsius, and then these panels are taken and tested to understand the deterioration, tested under tension, as well as sections of these are subjected to microscopic analysis to understand the attack of the alkali that is present in the cement around the textile. So these images show the direct alkali attack test, the expedited part, and that the one which we do with the composite shows the attack of the alkali that is present in the cement around the glass. So what is done to understand the properties of this matrix or the TRC is the study on the acid exposure. Why do we even need to do the acid exposure study? That is because I've said that these systems can be used as water retaining structures. So we work on utilization of these systems as small modular sewage treatment plants, which are very much, these modular treatment plants are very much used in European countries. So in our country, we are working on development of such tanks with the textile reinforced concrete. So what is essentially required is to understand whether the matrix and the textile will withstand the biogenic sulfuric acid which is formed in the sewer pipes, the closed sewer environment. So as such, in general, we know that these closed sewer pipes tend to get attacked in their crown portions because of this biogenic sulfuric acid which gets formed as part of the byproduct in the sewer lines, as part of the emissions. Right. So here we tend to understand whether this particular matrix and the textile is suitable at this environment or not. That is why we conduct the acid attack study on matrix. So the first image shows here the pristine, that is the concrete cubes of 70 mm size cubes which are exposed to the chemical acids. There are two types of tests that we conduct here. One is the chemical acid attack study, which is conducted in the laboratory, And the second one is the biogenic acid attack study, which is conducted in the real original field conditions itself. So in the chemical attack study, what we essentially do is use coated and uncoated specimens. The specimens which are shown in the tub here immersed are the uncoated specimens, that is the direct matrix cubes which are immersed in the in certain concentration of sulfuric acid solution. What we actually check is also what happens. We definitely know that the matrix get deteriorated at a point of time. So we should check if there is any coating or anything which can be done on this matrix in such a way that its deterioration can be delayed. We certainly cannot say that the deterioration can be stopped, but the deterioration can be delayed and the lifespan can be improved. So what we study are certain coatings. Here I've shown two types of coatings. One is a porcelain based coating, and other one is a coal tar based coating. And we are also into studying different types of coatings which will work on the matrix for this purpose. So the chemical acid attack study is essentially on understanding on a certain exposure period what is happening to these matrices, how they are getting their mass or the dimensions deteriorated or reduced or affected. In the biogenic sulfuric acid test, what we do is all these cubes, the coated and uncoated cubes are prepared and they are suspended in the crown portion in certain sewage chambers. So we actually identified certain sewage chambers where there is a good flow of sewage. And in the crown portion, we also checked for the presence of the pH. We check the pH at the crown portions to understand the sulfuric acid, that is the biogenic sulfuric acid presence. So what we did is we suspended these cubes in some of these chambers, and these are monitored. The one more difference is that the biogenic sulfuric acid or the real-time tests are kind of long-term tests. The more we expose, the more we understand, or the more period that we expose, the more deterioration it happens. And these are kind of long-term tests. These tests may run for like 3 to 5 years or even up to 10 years to understand the deterioration. So the chemical acid attack tests which are carried out in the laboratory are done to expedite, to understand quickly what happens in the system and to develop the service life models. So what we found on exposing these specimens, these cube specimens in acids, we found that the specimens on exposure to certain periods such as 4, 8, 12, 16, and now we are into 20, 24 weeks, we found that there is a certain mass loss and dimension change that is observed in these systems. So what we are looking at is the development of the service life models and the prediction of the lifetime for like over 50 years, what happens, over 100 years, what happens. So essentially this study looks at the development of the service life models for prediction of the service life of these systems. So what I've shown is a matrix here. Similarly, we do it also for the textiles and also for the composites. Coming to the applications of TRC, there are quite interesting applications of this textile reinforced concrete. If not in our country, many applications were done in different European countries. We can see, we can see quickly one by one. So the first here shows a roofing system which is present at Aachen University, Germany, RWTH, and we can see like in this system is around like 35 to 40 mm thick, and we can see a lot of people standing at the edge of this roof, and the roof still was found to sustain. And this was a pilot project which was developed, and it is still under use or still under observation in RWTH, and it was found to work well. So, certain curved parking elements in the parking space were also developed at RWTH, and they were also found to work well. As we said, specifically this material is used for the tensile or the panel or the modular kind of systems. So facade panels were developed using TRC and installed outside a couple of the laboratory buildings at RWTH. And we have our industrial partner called as Reina Industries in India, who work in India as a entrepreneur working on the development of these facade panels on a commercial scale. Again, this image here, it shows the external wall cladding in one of the school buildings at Dusseldorf, Germany. Parapet sheets. Parapet sheets were developed by the Technical University Dresden, where these modular sheets can be used as parapet elements in place of in situ constructions. These can be quickly taken and they can be positioned and jointed using proper jointing systems. And this image shows here is shows a diamond shaped framework, architectural framework, which was developed by RWTH again. And some furniture, some interesting furnitures, barbecue stands, said to certainly work well in the presence of the hot coal that is present inside. And we at IIT Madras, we also developed certain benches of say thickness around 60 to 80, sectional thickness around 60 to 80 mm. And these benches, we have put them for use around our laboratory around, it's been 4 to 5 years since we prepared, and they were found to work really well with all of the sitting and standing loads on them. Apart from these small elements, the Technical University at Dresden, they've also developed a segmental bridge, and they have developed the module which was developed in the factory or the laboratory. It is also placed across one of the channels in Dresden, and this was monitored and has found to work well. Yeah. So there are also these modular decentralized treatment plants, the sewage treatment plants. Unlike our cities, metro cities here, where we have the centralized treatment plants, in many of the cities and states in European countries, what they prefer and use are these decentralized treatment plants, where either these plants of smaller capacities are used at each home or within a cluster of houses. So these decentralized treatment plants are kind of famous in European countries, but not many were made with TRC. They are generally done with the regular RC until now. And now we are working with our institutional partner RWTH Aachen and also our industrial partner Beatenwork Henschel GmbH to develop such industrial, decentralized treatment plants to be installed in remote villages in India as part of our the Swachh Bharat mission of our country. We are into development of such plans, and we are into research, and the demonstrators are kind of getting developed. By mid of next year, there will be more demonstrators which will be installed in the Uttar Pradesh, Madhya Pradesh regions of our country as pilot projects. Yes, so the TRC is used for bank protection. The panels are used for bank protection. The panels prepared in the laboratory, and they are shifted, they are transported, and they are positioned as bank protection units. This TRC, as already mentioned, it is also used as a solution for repair, retrofitting, and rehabilitation. This picture here, it shows the repair of a sugar silo in Germany, and masonry wall retrofits were carried out as part of research by the Saint Gobain in India. Saint Gobain in India is one institute who produce these textiles, but from the fibers, the production happens in France and also in US. However, they are one point of contact if we want to get these textiles which were manufactured abroad, and they are also into research projects with this TRC. Strengthening of beams. The deteriorated beam is shown here. The mats are placed and they are closed or finished. Strengthening of unreinforced masonry chimney, where we find the crack here in the chimney. The textiles are placed around, textiles are wrapped around, and they are closed with a mortar here. These images show the strengthening of a bridge across the Rome-Formia-Naples railway line in Italy. The arch bridge here, the underside of the arch bridge is subjected to strengthening with the textiles, and finally it is finished, and this is also monitored for its performance. We at IIT Madras, we try to strengthen a couple of columns which were present in the Students' Activity Center, the biggest hall that is present, the auditorium that is present in the campus. There were we actually took two deteriorated columns and we worked upon it. What we did is we gave a 10 plaster on the hacked surface of the columns, and we placed the mortar, we wrapped the textile, the first layer of textile, gave the laps, gave the vertical as well as the horizontal laps here, because over the length of the over the height of the column we had to give three layers of three parts of textile, because these textiles were available only at certain widths, so we had to give certain laps along the vertical directions also. And we place the first layer of mortar, then the second layer of textile, second layer of mortar, and third layer of textiles and mortar. So we are also carrying out the research in TRC with respect to its very many applications. We are into development of treatment plants. We are into development of systems and the design part components of in terms of the repair, retrofit, and strengthening aspects as well. Finally, we were able to achieve a thickness of around like 18 in place of the concrete jacketing, which was done for certain other columns closer to these columns, which occupied like 50 to 80 thickness of jacket because of the steel rebars which were used. The 18 was a thickness which was achieved with the TRC. So in places like this, there is also a saving or a clearance in the space. There is not much space occupied if we are looking into the strengthening of these elements. We are coming to the end of the talk. Here I want to summarize or to touch upon the sustainability aspect of the textile reinforced concrete as well. So this material, because of its properties and because of its properties, it has a higher potential for substantial optimization of materials because of all the details that has been shared until now. So the components were set to provide proper service life, and these are expected to be much longer than the conventional reinforced concrete in the absence of steel and with proper engineering. And hence, due to all this, the lifespan of the existing structures were found to be extended. Looking into the embodied energy per unit volume of construction materials, the embodied energy is nothing but the energy which is consumed to form a material or to make an element, to manufacture a material or to produce an element using that material. This embodied energy, as low the embodied energy is, the lesser the energy is consumed, the lesser is the carbon dioxide emission or the effect of global warming. So what we see is, compared to the steel or the GFRP or the timber or the RC, the TRC is found to kind of show a lesser embodied energy as such, with less energy in its life cycle, lesser environmental impact, and lesser greenhouse gas emissions. So with this I stop. So thank you for patiently listening to my talk for over like 50 minutes. We can take up the questions if there are any. Thank you.
Thank you, ma'am. It was really an interesting session. The time invested on this webinar is really worth it. Any queries can be typed in the chat box. Komadi ma'am will clear all your doubts. Any queries can be typed in the chat box. Komadi ma'am will clear all your doubts.
Whether it is completely not understood or clearly understood, I don't know. Isn't it?
Well, I think the session is very much crisp and clear, so there is no doubt, I think.
Okay. If it is clear, then I'm really happy about it.
Yeah, Dr. Kamadi, you have done a good session and things were quite lucid.
Thank
and
you.
obviously a material which may catch the market soon. Like when the gypsum boards came into market, it was a bit reluctant for the people to accept it, but now it is accepted. So the TRC also will catch the market, I think, soon. So thank you very much for presenting a nice session.
Thank you, Professor. Thank you.
Now, I welcome Dr. P.R. Sri Mahadevan Pillai, sir, to hand over a virtual memento for Dr. Komadi Murugan ma'am as a token of love. So please.
Pardon? That arrangement is made on screen? Okay.
Yeah. Okay, sir.
Yeah, thank you very much. Thanks for the kindness and memento.
Thank you, ma'am. Thank you, sir. Next, I welcome Mitra of S3 Civil for vote of thanks.
Good afternoon, all. Respected and distinguished Chief Guest, Dr. Komati Murugan ma'am, respected Principal, Dr. Sri Mahadevan Pillai sir, staff coordinators, and my dear friends, it seems to be a great privilege to propose the vote of thanks to all who have helped in making this webinar a very resounding success. First of all, I would like to give my hearty vote of thanks to our Chief Guest, Dr. Komati Murugan ma'am, for gracing today's webinar. Thank you, ma'am, for your very informative session. And next, I would like to express our deep gratitude to the Principal, Dr. Sri Mahadevan Pillai sir, Vice Principal, Dr. Krishna Kumar Kishore sir, and Head of the Department, Kripa ma'am, for your presence in this session. I would also thank our beloved staff coordinators, Dr. Mahima Ganeshan ma'am and Ms. Shruti Ravindran ma'am, for their guidance and moral support. I am happy to express a vote of thanks to our faculties that has made this webinar a grand success. Finally, I thank the wonderful participants who have turned up in such great numbers. Once again, I thank all for your cordial cooperation. Thank you.
Thank you, Mitra. All the participants are requested to fill the feedback form. Thank you everyone for kindly attending the webinar. Thank you.
Thank you very much.
Thank you, Gomadi. Thank you. Thanks a lot for coming.
Fine, that's fine. Thanks. So I can leave, right?
Yeah, right.
Yeah, fine. Thank you once again. Thanks to Professor. We'll see. Bye.
Yeah. Participants, please fill the feedback form for the certificates. Thank you all for joining.